hey, I started erasing things. Probably shouldn't have because um, I don't want to go through that again. And neither should you. So this formula right here, make sure you have this written down and you'll see why. Or if you have fantastic memory, go ahead and memorize it. Now we're working with this. And now we want to solve ultimately for x. In other words, we want to get a formula for x in terms of the original coefficients. And hopefully you got it. Remember last video I said work on it. Let's go ahead and do it. Now remember, if I initially solve for x and I make the substitution, then I get this. So let's initially, I want to leave this here. I know it seems strange, but I want to be able to take a look at this in a minute. Let's solve this for y. So we would get b sub 1y equals c sub 1 minus a sub 1x. Hey, the better you get at this, or the more you do with these, you'll develop your own style for writing this down, and that's fine. So you don't have to adhere, like I said before, to the format that I'm using here. Let's divide both sides by b sub 1, and we get y equals c sub 1 over b sub 1 minus a sub 1 over b sub 1 x. Now I may start writing this in different ways. This is a sub 1x over b. This is a sub 1 over b sub 1 times x. They both mean the same thing, so you write it however you want. Let's go ahead and add these two together. And, let me get something to erase here with. I wrote it like this, which in a way is kind of nice because it's in the y equals mx plus b form. However, just for a change of pace, or maybe because I'm looking down the road at something, but let's go ahead and write it like this. Which is maybe how you wrote it in the first place. So fine. Let's make the substitution. We'll substitute this in for y in the other equation. So a sub 2x plus b sub 2. Now y is equal to this. Here's the substitution step. Let's see. So I have to copy everything carefully and not make a mistake. We get that? Now we want to solve this for x. We want to solve this for x. So let's go ahead and multiply this out because we like doing the distributive rule, because we always do the distributive rule. Now, when I multiply this out, again, there are many ways you could write this. There just are. And some are easier to deal with than others, depending on the situation. So let me go ahead and write it in a particular way, and hopefully you all see how I did this. It shouldn't be that big of a deal. Minus there's a lot of symbols on the board. I get it. There's a lot of things that I've written down, but oh, hey, I should finish the equation. C sub 2. Now let's group together like terms. So we have this of x and this of x. Let's factor the x out. We get a sub 2 minus a sub 1 b sub 2 over b sub 1 all of x. And I don't have much room here. Let's go ahead and subtract this from both sides. So equals, I don't have enough room to write this down right now, so I'm going to erase this term here. Just give me some room. So these two we just put together, factored out the x. This term right here that I'm covering up, I'm subtracting from both sides. So what will we get over there? We'll get c sub 2 minus this term. I could leave it, I could just leave it written like that, but b sub 2 c sub 1 over b sub 1. Okay. We can always, you can just rewind and get that. Like on the last video, look at this. This is sort of complicated, I suppose, or complex looking. So you may not know what to do. Remember, if in doubt, do the distributive rule. Factor something out. Combine like terms. If you see fractions that can be added or subtracted, add or subtract them. These are things you do as a habit, like I've said, as a reflex. You're not, maybe you don't even know why you're doing it. Maybe because you don't know what else to do. They're good things to try. So let's go ahead and add these two up here. Remember, there's a one under there, the usual business about fractions. So we get a sub 2 b sub 1 minus a sub 1 b sub 2 divided by b sub 1 x. Uh-oh, wait a minute. Let me see. Can this be seen? Let me write this a little bit lower. Yeah, I'll write it down here like this. So from here, right here, this is a sub 2, b sub 1 minus a sub 1, b sub 2 divided by b sub 1 x equals, over here let's do the same thing, b sub 1 c sub 2 minus b sub 2 c sub 1 divided by b sub 1. And let's divide both sides by the coefficient of x. How do we divide? We flip and multiply. I'm not going to need any more of this. I may want to, or I will want to refer to this. So let me leave the original problem up there. When we flip and multiply, the b sub 1s are going to cancel out. This b sub 1 will cancel out with that. And what we'll be left with is this. X equals b sub 1 c sub 2 minus b sub 2 c sub 1 divided by a sub 2 b sub 1 minus a sub 1 b sub 2. Now, what do we have? Well, we have a formula that flat out tells us the solution for any two equations and two unknowns problem. It says if you tell me what these six numbers are, the first coefficient of x, first coefficient of y, the number on the right, first number on the right, second coefficient of x, second coefficient of y, second number on the right. If you tell me what those numbers are, we could directly plug them into this right-hand side here. You just plug the numbers in and plug the numbers in over here. Presto, you get an answer. Maybe certain things come to mind. One would be, well, this is great for a computer for writing a program. You just write a program and the program asks for these six numbers, plugs it in those two formulas, and without doing any algebra. I mean, you've done algebra. Look, you had to do algebra to get these formulas, but now that you have the formulas, you only have to do arithmetic to get the answers. And if you're a computer, that's fantastic. So we could see a practical use for these formulas. Now, what's the downside? Well, it kind of makes your eyes blurry or makes your head hurt to look at this. B sub 1, C sub 2, B sub, look at all, I mean, how are you going to remember that? Well, I'm not asking you to remember it. Most teachers do. I'm not going to. I don't normally anyways, and since you're home, you could just presto look it up anyways. But what's going on, what's going on here? Is there some sort of a pattern? Well, I need some space here, and yet I don't want to erase any of this. Consider this original system of equations. Just consider that. What changes from one problem to another? What changes from one problem to another? It's these six numbers. The x's and y's stay put. It's just the numbers that change. So in a way, if I just write down the numbers, a sub 1, b sub 1, c sub 1, a sub 2, b sub 2, c sub 2, those six numbers completely determine the problem. I can dispense with the x and y. I mean, they're there, and we know they're there. But for writing down the problem, in a lot of ways, I could just write this array of numbers down. Like I said last video, this array of numbers is a matrix. It's a rectangular array. Here we have 2 rows and 3 columns. And I hope you can see how this system of equations determines this matrix, and this matrix determines the system of equations. And we can actually look at them as being the same thing. I mean, I guess if you know this, you absolutely know this. And if you know this, you know this. So if you know one, you know the other. They're the same thing. I'll have to think about the logic of that for a minute. And this means we have two formulas to solve this system in terms of this matrix. Now, I bet a lot of you have seen this before. I almost wish you hadn't. Because if you've never seen this before, still, this can make your eyes go fuzzy or make your head hurt or, whatever cliche you want to use. How do you make any sense out of this? Well, let's start here with x. You multiply b sub 1 and c sub 2. So you multiply these two, these across from each other diagonally, and then you subtract these two. So you multiply these two and subtract these two. What I mean is you subtract the product of these two from the product of these two. I mean, you can say it in a whole bunch of different ways, but this times this minus this times this. Now, this pattern may just seem like a triviality or may seem like some, geez, I can't think of the right word here. Just like some quirky little thing that somebody made up, take this times this and subtract this times this. Well, it turns out that this is a pattern that comes up over and over and over and over again. And it comes up so often that first off, we realize, it's some sort of a thing. It's some sort of phenomena occurring here. Secondly, maybe we want to give it a name, and we do. I want to just look at this square right here. B sub 1, C sub 1, B sub 2, C sub 2. If you multiply these two together, B sub 1, C sub 2, and then subtract B sub 2, C sub 1, and you determine this, you calculate this. This is called the determinant. Well, it's the determinant of a 2 by 2 matrix. Again, I think the first time that I saw this, I thought, wow, this is a lot of hoopla. This is a lot of effort. And you even have a fancy name, the determinant. In fact, it's the determinant of a matrix. And we get this. It seems like too much effort for what you get out of it. Because after all, let's go back. We could just solve these with substitution, or we could solve these with elimination. So we already have two perfectly good methods for solving this system of equations. This seems like a lot of extra effort, and honestly, it is. And if there were no other reason to consider things like this and these, if there were no other reason, nobody would do it. But there are other reasons. There's lots of other reasons, thousands of, I don't know, millions of other reasons. Actually, yeah, millions of other reasons. Now, let's take a look at what we have here. Oops, wish I didn't erase that. What's going on down here? A sub 2, B sub 1, A sub 1, B sub 2. Let's just consider, just this portion of this coefficient matrix. Just A sub 1, B sub 1, A sub 2, B sub 2. Incidentally, not incidentally, I mean, I'd like you to see these subscripts. This is row 1, row 1. This is A of row 1, B of row 1, A of row 2, B of row 2. Now, there are other ways to write this, but this will work pretty good for us right now. What's the determinant of this 2 by 2 matrix? The way you find a determinant is you take this times this, A sub 1, B sub 2, and you subtract that. Well, that's what we have down there. Now, I can write this, or let me just say this right now. Let me just speak this. To find x, you find one determinant and you divide it by another determinant. And, which determinants do you use? Well, we're solving for x, and it turns out that if you cover up the column which corresponds to x, the column, that's the determinant you use for the numerator. This right here is the determinant of the matrix you get when you cover up the coefficient column, the third column. Look at this down here, A sub 1, C sub 2, A sub 1, C sub 2. If I covered up the column associated with y, then that numerator is the determinant of the resulting 2 by 2 matrix. and the denominator is the same. So in words at least, it's one determinant divided by another, a different determinant divided by a determinant. It's the determinant you get by covering up the x column divided by the determinant you get covering up the coefficient column, or this third column. And y is the determinant of the 2 by 2 matrix you get by covering up the x column divided again by the determinant of the 2 by 2 matrix you get by covering up the coefficient column. Again, this probably, if you haven't done this before, this probably seems unnecessarily complicated. I'm smiling now because I'm going to let you know tomorrow whether we're going to want to push this idea of determinants to solve systems of equations into the realm of 3 by 3. It's very analogous to this. It's also analogous to the way the amount of work you had to do to go from 2 equations and 2 unknowns to 3 equations and 3 unknowns, it jumps up exponentially. And it does. And that can be very, very unpleasant. And you can get what's called combinatorial explosion, which just really means, could you imagine going to 4 equations of 4 unknowns and 5 equations of 5 unknowns? You might think, wow, the amount of work goes through the roof. It does. It gets, quite frankly, almost unbearable as a human to solve. Rare is the time that I ever by hand solve anything beyond 3 equations and 3 unknowns. Are there uses for this? Yes, there are, and I'll talk about some in an upcoming video. Without telling you any details, or any, like, how the heck would that ever possibly work out? Most airlines, when they schedule their operations, they wind up solving systems of tens of thousands of equations with tens of thousands of unknowns. And if you think that's impossible to do as a human, yeah, it is, or I believe it is impossible. I don't know if you spent every waking moment of your life and lived to be well over 100 if you could do it. I don't know. I'd have to sit down and do the math. But it's untenable, if not impossible. Okay, I'm going to leave this video here for now. We're going to continue on a little bit more with this. There's a little bit more terminology that I want to introduce and would like to have you know. But for right now, what did we do? We started off with a general 2 equations and 2 unknowns. We used the relatively simple method of substitution. I should say straightforward. I mean, there's a bit of work, but the idea of it is relatively straightforward. We generated these 2 formulas. We made some sense out of these complex formulas by finding a pattern. And the pattern is something called a determinant. And if, depending on, where your life takes you, this is something you may never see again or may see again many, many, many times. Okay, that's enough for this video.